Hello, my name is Jason Nakla. I'm a developer technology engineer with AMD, and today we're going to look over a number of effects, libraries, and tools that are available for download on the newly relaunched GPU Open website. Now, GPU Open has been around roughly since early 2016. Is really set up with the goal of being competitive and open source sort of middleware marketplace where we could publish a number of software modules and libraries to really make it easier to increase software portability between video game consoles and PC and high performance computing. Now, the software modules on the site were grouped under a number of umbrella headings like effects, tools, and SDKs, libraries. We also had a section for patches and drivers, along with some driver source code for Linux users. And all of this was always made available free of any sort of black box implementations or any licensing fees. And most code samples would be available on GitHub. Now, this was a convenient one-stop shop for all your sort of latest information on effects that AMD was putting out, as well as up-to-date GPU and CPU information, along with upcoming and past events, so you could download presentations we had been giving at previous conferences. But recently, the site's really been showing its age. It's 4 years old now. So a relaunch effort was sort of kicked off in order to redesign the site. Which leads us to the relaunch of GPU Open this week, where we've drastically modernized the site to really try to streamline getting the information that matters the most to users front and center. This includes some of the latest news, what we're promoting as popular topics each day on the site, a lot of our valuable technical blogs and samples. We've polished a lot of these and really given them a new place in a Learn section that are much easier to access from the get-go. And from the launch, we're also adding exclusive new content from AMD engineers who are making a lot of their tips and tricks that we use internally available to developers for the first time. And the site even looks good on mobile. And on top of that, with the relaunch, we're also launching a new social media presence on Twitter. You'll often be able to see updates and frequent postings alerting users to new and interesting topics, as well as any new libraries or other information that will show up on the site. So with that said, let's take a look at just a few of the new effects and libraries and tools that you can find on the new GPU Open. So the first thing we're going to look at are just a number of more recent effects that we've recently put out. And we're going to start with TressFX. TressFX is one of our longer running series of effects that we've been publishing. And TressFX 4.1, which was recently released at the beginning of this year, offers the very first implementation of TressFX on Vulkan, as well as a reorganization overall of the effect to make it a lot more efficient on both Vulkan and DX12 APIs. A number of optimizations have been made, both to the simulation and the rendering passes. These include faster velocity, shock propagation calculations. We've simplified the local constraints, or the local shape constraints calculations. And more importantly, we've also reorganized the dispatch and barrier groupings to increase performance and make things a little more performance friendly. Now, on the rendering side, we've added support for strand-based UV texturing, and as well as hair reduction through a dynamic LOD scheme. And the new sample will also ship with a brand new exporter for Autodesk Maya. Now, the release of TressFX 4.1 also marks the first time that we're releasing an Unreal Engine integration of this effect. Currently, the effect supports Unreal Engine 4.22 through 4.24. The code is set up as sort of an external module and only needs about 4 or 5 hooks into the underlying engine, so it's fairly simple to use and set up. The bulk of the integration focuses mainly around the simulation part of the hair, but we've also included a simple reference renderer just to give developers who are looking to use it a starting point on getting TressFX integrated into their Unreal-based games. Features in our implementation in Unreal include a self-contained TressFX component, which will handle simulation and reference rendering of the hair. We've added UAsset support for TressFX data files, which can be imported just by dragging and dropping assets into the engine, just like you would any other type of UAsset asset. Hair shadow rendering is done through Unreal's own shadow system, though because of integration limitations, we can only support shadowing for dynamic lights on the hair, so just be aware of that. And lastly, we've implemented an interesting parameter blending scheme through a series of blend maps to allow a little more flexibility in how to apply color and patterns to the hair. So with that said, let's take a look at a demo of TressFX 4.1 in Unreal 4. In this demo, we're going to have a look at just how easy it is to get your TressFX geometry from Maya all the way into Unreal Engine. Now, I have an existing scene here in Unreal that was created for the purpose of our TressFX integration. This character's name is the Old King, and as you can see, he's already got a few hair components on him already. But right now he's missing a crucial part to the model, and that is his facial hair, so his beard and his mustache that you can tell from the underlying 5 o'clock shadow texture here. Now, before going into Maya to export your geometry, do make sure that you've copied your TressFX exporter plugin into either your local Maya plugin path for whatever version you're using, or the global plugin path, which can usually be found under Program Files. So we'll pop into Maya here, where I've got the character preloaded with all of its hairs hidden away for the moment, just for performance reasons. Now, before also starting in Maya, do go under your settings preferences in the plugin manager and make sure to load the TressFX exporter. You can also auto-load it for convenience for the future. What this will do is it'll add a nice little TressFX menu in the menu bar from which you can export all the data that you need to. Now, normally when exporting a model, we would also export a collision mesh with that model to drive the sign distance fill collision. It's already been done for this model, so in order to save time, I'm going to skip that step right now. Though note that it is amply documented in the PDF information that we ship with the TressFX integration code on GitHub. So I'm going to start by unhiding the geometry that we actually wish to export. In this case, the beard and the mustache. So we will go ahead and just show that information, and then we will bring up our TressFX exporter. Now, whenever exporting our hair information, we also need to set a base mesh. This base mesh is used to drive how we collect the UV information for the roots of the hair, and also how we pull out the skinning data. So I have an underlying mesh here that is already in the scene. We're just going to set that as the base mesh and go on to choosing our options. Now, I actually want this to be a little finer for simulation purposes, so we are going to have it export 32 vertices per strand rather than 4. And because the beard is kind of bushy in this scene, we don't really need a one-to-one representation, so we're just going to sample every second curve that Maya has and essentially generate a half-scale LOD model for this. And we're not going to touch the scale scene information, as it should already be correct for this scene, since this was all set up for this demo. Now, because we are working in Unreal, make sure to check the Make Z Up direction option. This will make sure that all of the data exported is in an Unreal-friendly format. And also, because we're using DirectX 11 and 12, do invert the y-axis of your UV coordinates, otherwise the UVs will come in inverted. To export, simply select the pieces of hair geometry you want to export, hit the export key. This will lump everything into one TressFX file. In our case, we've already got a number of files that we've exported with different LOD settings. So we've previously exported a lower LOD of this, We're just going to reuse the naming convention and rename this to S2V32 since we are now sampling every second curve and not every fourth curve, and we'll let that save out. What this will do is save a TFX file. The TFX file represents all of your vertex strand information as well as your UVs, things like that. And then once this process is done, it'll pop up another dialog for us to also save a TFX bone file. The TFX bone file is what's going to tell the hair, give all the hair all of its skinning and boning information that it can use to do the skinning part of the simulation. Alright, now that's done. We're going to repeat the same process for the bone file. Note, it's not necessary to name the file exactly the same way. You can name this file whatever you want. The only thing to take into account is when you're importing it into Unreal, you will have to make note of the whatever file name that you saved it as to make sure you're pointing to the right file. Now, right now, this looks like it's done, but this is actually still working in the background. What happens here is the progress bar just gets loaded behind this dialog and as another one is spawned in. So we're just going to give this a few seconds. It will finish the skinning export, and then we're going to pop back into Unreal to import everything. Alright, with that done, we go back into Unreal. And the first thing we're going to want to do is bring in our newly exported TressFX data into Unreal and import it as a TressFX U asset. Now, we've already got a directory where we have a number of existing assets. In fact, I had previously imported it, so I'm just going to actually delete this right now. And we're going to bring in the one that we just exported. So if I take our newly exported S2V32 asset, I'm going to drag this in here just like any other U asset. This is what I was mentioning. If you've named the bone file separately, do make sure you path it to the correct file on import, otherwise you might have some problems. There are also some procedural hair options that we have here. We're not going to touch these right now. We just really want a one-to-one representation of what we've exported out of Maya. And then lastly, we're going to point this to the Old King skeletal mesh. This is so that Unreal knows what boning information to help drive the skinning. We will import that, and then that was imported into Unreal. And then we will also create a TressFX component for this. We'll go into Unreal, Blueprint class, and we will just search for TressFX component, create a new TressFX component, and we will name this Old King TressFX comp stash beard. Now if we open that, you'll see that everything's just bare bones and empty. That's fine, we're going to leave it like that for now. So that we can see what happens as we change this data afterwards. So then we're going to go into the Old King's master blueprint. Under the skeletal mesh, we're going to add a new component. We're going to search for our TressFX component that we just added. So here we have Old King TressFX comp stash beard. We're going to add that in, maybe give it a better name. And you see that it's still empty and nothing has really changed. So the first thing we're going to do is we are going to point this to the asset we just imported. Now as you can see, it's looking a little rough for wear. It doesn't really match with what's in the scene. That's just because we need to point this to some additional data that has previously already been set up for this model that I will go ahead and set up now. and point it to a base albedo texture. We also have a number of hair parameter blending options in Unreal. We're going to skip this for now. It's not really important for the purposes of this demo. We are, however, going to enable the Strand UV. This creates an additional layer of hair information, another set of UVs that lets us do UV mapping individually on each strand. We're also going to tile our hair, our UVs, just to add a little bit more repetition to it. And then lastly, parameters used to drive TressFX, both rendering and simulation parameters. In Unreal, we've actually grouped these into their own parameter structures to make it easier to import and export them. So I'm just going to go ahead and actually assign this to some pre-existing parameters that were previously set up. And as you can see, this is looking a lot better now. There's just one last thing we're going to do. Make sure that this is casting shadows so that we get nice sit in with our scene lighting. And lastly, one more thing I'm going to do is we have some logic in here set up to drive the wind into the simulation just to get better simulation out of it. So I'm just going to go ahead and hook this back up really quickly, so that this will take part of the overall scene. There we go. Compile and save that. Now everything is hooked up. And if we go ahead and play this, we see that now our character is complete. And that will do it for this demo. Thank you. And that was TressFX for Unreal Engine 4. Now the next few samples I'm going to talk about are new entries into our Fidelity Effects library of effects. The first one we're going to visit is Fidelity Effects SSSR, which is a high-quality stochastic screen space reflection implementation based on an industry-leading algorithm and tailored for efficiency and speed for RDNA architecture. Now this sample uses a hierarchical depth buffer in order to create a traversal kernel, and we use this to trace rays into the scene. Now, the rays are jittered to simulate glossy surfaces with varying degrees of roughness, and higher roughness will essentially mean more spread out rays. This also marks our first sample built for Navi and for RDNA that ships with a high performance spatial and temporal denoiser. The sample itself makes use of HLSL Shader Model 6 to add wave level optimizations, and it's currently shipping on D3D12 with a Vulkan version coming soon. Requirements for the effect are fairly modest and are made up of information that most modern engines already have on hand. This includes a depth hierarchy, downsampled by a factor of 2 for each level, which, as a preview for something I'm going to talk about later, is a great candidate for work by our single pass downsampler, which will make very quick work of this. Per pixel motion vectors, the resolved and lit scene, normals for the current and the previous frame, as well as roughness information for the current and previous frames. Now the algorithm itself works as a set of 3 major passes. The first is a tile classification pass. This consists of a compute job that will identify what pixels need rays generated for them, help identify rough versus mirrored surfaces, and decide which tiles need denoising. Now, this will batch up work for later passes that will be executed via indirect execution. And the temporal denoiser pass at the end of the entire frame can also be used to spit out a mask that can identify what pixels are temporally stable. Now, if the classification pass finds that a certain pixel isn't temporally stable yet, we can then force an additional ray for that pixel during tile classification. The second pass is the intersection pass. So when one is needed, this will trace through the depth buffer hierarchy and find the first intersection. Failure to find an intersection will just fall back to the environment map. The surface glossiness information is used here to help apply a variable rate traversal scheme to our reflection lookup, where we will essentially do 1 ray per pixel for perfect mirrored surfaces, but we'll only use 1 ray per roughly 4 pixels for rough surfaces. We then run our generated reflection through a series of denoisers to coalesce and stabilize the results. Now, the denoising of the image takes place over 3 separate denoiser passes. The first is a spatial denoiser pass that works by taking 16 samples of a Halton sequence over a 7x7 kernel region. We use the normal as an edge stopping weight and a Gaussian weight based on the differences in the depth. So we accumulate all of these radiance values and then we normalize them using the accumulated weight information. And we'll then apply the second pass, which is a temporal reprojection pass, based on either the surface position or the hit position of the image in order to stabilize it. Now, the best results we've seen so far seem to come from using the surface position reprojection for rough surfaces and using the hit position reprojection for very reflective surfaces, and this while using a simple constant as a cutoff value. Lastly, we'll run an edge-aware Atrou filter to get rid of any remaining spatial noise. So having said that, let's have a look at what it looks like. Next up, we're going to look at a new screen space ambient occlusion implementation for our Fidelity Effects library. Fidelity Effects Kakao, or Combined Adaptive Compute Ambient Occlusion, is a new highly optimized implementation of Intel's adaptive ambient occlusion for RDNA. This sample features multiple settings that can be played with in order to balance performance versus quality, depending on what other workloads you might have present in your game. You can run it simply with the depth buffer or with additional normal buffer information for a better result. The sample is currently only implemented on DX12, but a Vulkan version is in the works and should also be releasing soon. So with that said, let's have a look at what it looks like. And that was Fidelity Effects Kakao. Next, we're going to have a look at Fidelity Effects LPM. This stands for Luma Preserving Mapper, and this effect is a tone mapping and gamut mapping solution for high dynamic range and wide gamut content. LPM works by tone mapping the luma of the RGB pixel, while ensuring that the result this produces is similar to the luma of the tone map of the RGB pixel. As such, there's a number of benefits that can be gained from integrating this effect into your engine. First and foremost, this can be configured to work with any positive RGB input color space. We can also configure it to then target any RGB output color space, effectively allowing you to target any display you would like to support. Now, to make this a little easier, the sample also ships with a number of pre-existing presets to target the most widely used color spaces. These include Rec 709, P3, Rec 2020, HDR10, and of course our own FreeSync 2 format. LPM is a completely ALU-based solution, which means it's a great candidate to run asynchronously on the compute queue. And lastly, in order to support better performance on Vulkan, LPM also fully supports FP16 operations. It's available now for D3D12 and will be coming soon for Vulkan. With that said, let's have a look at LPM. The next sample we're going to look at, this is actually our first sample released under the Fidelity FX banner, is CAS, or Contrast Adaptive Sharpening. This was created to help fix image contrast lost to temporal anti-aliasing algorithms. It does this by providing a more of a natural sharpness without creating any additional artifacts and with a very minimal performance overhead. We've also created this to factor in upsampling, especially in games that do dynamic resolution scaling. So this can also be used to help lighten your GPU workloads and get faster frames without having to sacrifice too much quality. So this works by using a single compute dispatch call that has been highly optimized for RDNA. So to get a better idea of just how this translates into improved visuals, so here's a scene from Borderlands 3 where we compare the same location with CAS disabled versus enabled. And if you look closely, you can really see sort of like in the back of the wall there, the pattern, the tiling pattern really comes out and sticks out more. We can really see it a lot more clearly with Fidelity FX. The last thing I'm going to talk about under the Fidelity FX group of software is the single pass downsampler. The sample is really just a showcase for a convenience library that we've created to allow game developers to create downsample chains from 4K all the way down to 1 as quickly as possible on RDNA. This works by taking a user-defined minification algorithm. So you provide it with either mipmap, histogram, luminance, whatever. And we schedule the work to happen as efficiently as possible using wave operations and or LDS over a single dispatch call that'll generate the entire chain or all levels in one call. This sample ships with code for both HLSL and GLSL. It also supports the use of FP16 operations if you want to make use of them. And if we look at just a simple example comparing the generation of a mipmap chain from 4K by 4K down to 1 by 1, which is roughly 11 generated images. So what I did when grabbing these numbers is I ran the single pass downsampler against a traditional just nested pixel shader approach of doing one downsample per pixel shader pass versus the single pass downsampler. So on a Radeon RX 5700 XT, the single pass downsampler version runs in about 3/4 of the time that it takes to do the same thing with pixel shaders. Now, when you factor in the number of buffers that you will usually generate MIP info for in a game, this actually translates to really good savings. The next thing we're going to look at is our FEMFX library. Now, this is a physics-based library used to compute motion for deformable objects. There's a few methods you can use to compute deformable objects, but FEM, or finite element method, is more physically accurate and easier to control compared to other methods. But before going into the details about this library, let's just go over a few FEM fundamentals. This is at its core a simulation. The input for our simulation is a tetrahedral mesh, which is shown here in the slide. The parameters on which we're operating are stiffness. There is a volume preservation parameter. We have a stress limit before permanent or plastic deformation, and also a stress limit before we fracture the object. Now, by using FEM, we can simulate all sorts of different effects that we couldn't before, such as bending metal, wood flexes and breaks, compression and bouncing. We can also do melting effects. And FEM simulation can improve a lot of the fidelity of the animations that we play back, and opens up a lot of possibilities for new types of interactions with the objects in our games. So to get a better understanding of just what I mean by this, let's have a quick look at just a small couple of demos that'll help you understand what it can do visually. The first of these is this car demo. So you'll see that if I sort of run this, the car itself is a FEM object, and by dropping weights on it, we're able to make it deform in a realistic fashion. We have similarly applied FEM to another model here, this time of a board to show off more braking deformation styles of interactions. Our FEM-based library is called FEMFX. We're releasing this open source on GPU Open. It includes a highly optimized multi-threaded CPU implementation, which will scale very well with many CPU cores. This is actually based on threading building blocks. You don't have to use this if you don't want to. You can stub in your own multi-thread or threading library. It's just there for convenience. We also release a Houdini plugin to author FEM objects, as well as a UE4 plugin, just as an example of how to do an engine integration. With regards to implementation details, we essentially do implicit integration, which will help to improve the convergence, especially for stiff materials. We have a constraint-based contact model between objects, which makes it possible to make our FEM solver compatible with rigid body solvers, so it's easier to integrate into your engines. Continuous collision detection is used to capture hits between fast objects, think things like bullets. And we lastly have multiplicative plasticity to model a more realistic plastic deformation. So this library, as mentioned, is highly parallelized, all built on a task system on threaded building blocks, where we will just spawn one task and then that task will span multiple tasks from itself. And as previously mentioned, this implementation isn't tightly coupled with the task system itself, so you are free to use any task system that you may already have into your engine. With regards to rendering, we currently offer the Unreal 4 engine plugin that we ship with the sample. This is just to show a sample integration of how you would go about using this. But in short, we prepare two meshes for FEM objects. One is the tetrahedral mesh that we use for simulation, and then we have a separate render mesh. This allows us a lot more visual detail compared on the actual object compared to the simulation. We often want to decouple these for performance reasons. Now, runtime, rendering vertices in the artistic mesh is driven by the tetrahedral mesh, and we just use their weights as through a pre-compute. This is actually very similar to how we would do skinning. In fact, it's pretty much the exact same procedure. Also note that if you are going to be fracturing your meshes, you do need to author your rendered meshes into pieces so that you don't have any seams or leaks in your mesh once you fracture it. The next item I'm going to talk about is ProRender. Now, Radeon ProRender is a powerful physically based path tracing rendering engine, which is written using OpenCL and Apple Metal APIs. It's been made so it runs on as many devices as possible. So if the device supports OpenCL or Metal, it'll just work out of the box. There is also a pure CPU implementation, however, so that even if you don't have a GPU which supports those compute APIs, ProRender will still work with that on the CPU. We support all three major OSs, Windows, Linux, and Mac OS. We distribute ProRender under two different forms. The first is as a plugin to most widely used 3D content creation tools, or as a direct integration from our partners, so like Maya, Blender, etc. We also distribute Pixar USD Hydra delegates, so they can be used in an application which will support USD and Hydra, like Houdini 18, for example. Another distribution form we now have is our of ProRender is our SDK, which a developer can take and integrate directly into their own applications or engines or tools. We're right now making the SDK public at GPU Open, so anybody can make use of it. And also we're also releasing Radeon ProRender 2 at the same time. This is actually a complete rewrite of the engine for a better user experience. And though there's more than a fair share of improvements to list, just to highlight a few, some major improvements are, especially in terms of rendering speed improvements, those have gone up a lot. GPU memory reduction, as well as support for Material X. Now, fully path traced images look really nice, but they do also take a long time to compute, depending on what you're doing with them. So, for example, it's too slow to be using a fully path traced image in a viewport for a 3D content creation tool. So with this in mind, we've developed a faster version of the engine, which we call Radeon ProRender Full Spectrum. What this engine provides is a parameter that you can use to adjust the rendering speed and the quality. So we have 3 rendering modes implemented in this engine: rasterized, hybrid, which is rasterization plus some ray tracing effects, and biased, which is a rendering mode which is based on a full path tracing, but will omit some computations to make it slightly faster. The next Radeon library we'll look at is Radeon Raise. This was released a while ago, and we've been seeing a lot of adoption in the industry with regard to Radeon Raise. So this year we're releasing Radeon Raise 4. Previously with Radeon Raise 3, we'd added a Vulkan implementation, as well as GPU accelerated BVH building and half precision computation support. Previous version to that was implemented in OpenCL. And one place where we've been seeing a lot of adoption of this is, for instance, in Unity, where people are using it to do GPU light mapping. Now in Radeon Raise 4, we're trying to make life a little easier in a world where everybody is defining different ray tracing APIs. So as it stands right now, with regards to ray tracing, we have DXR, there is Vulkan compute and ray tracing extensions, there are metal performance shaders. Now the API for Radeon Raise 4 is much cleaner, just one-stop shop API designed to sort of bridge and wrap around all other platforms and be API dependent, at least as much as possible. So it does give you a few options on how you can use ray tracing for whatever scenario works best for you. Now, we actually have 3 different API modes to choose from. The first one is for batch intersections. This is essentially the standard SDK that was provided in previous versions of Radeon Raise. So if you're happy with that, you can just keep using that. The second is an API which allows us to make use of the DXR 1.1 compute shader intrinsic. Because Radeon Raise builds an accelerated BVH structure, we can traverse through this with DXR and makes this a possibility. And if you want even more low-level access than that, you can actually write your own BVH traversal logic as we open up the format to the BVH data structure. We're thinking this is going to enable certain algorithms that right now we can't do in DXR API. And the last library I'm going to introduce here is Radeon Image Filter Library. So as the name suggests, this is a collection of post-processing filters, mostly tone mapping, denoisers, bloom, so on. We're also releasing our AI or machine learning based filters, specifically our AI denoiser and upsampler. So an example of this AI denoiser is shown on the right here. So the right hand side of the image is the input for the denoiser, so the image to be denoised. And then the left side of the image is the image that is spit out by our denoiser. The image filter library is implemented on different GPU compute APIs, so including OpenCL and Metal. And the version we released recently includes both DX12 and DirectML for machine learning filters. The last thing we're going to look at today is some of the tools that we use to build out these effects and samples to be as performant as possible on our hardware. The first tool we'll look at is the Radeon GPU Profiler, or RGP. So this is really our go-to tool whenever we need to understand GPU behavior. RGP will give us a fully detailed picture of exactly what's going on GPU-wise within a rendered frame. So this includes looking at occupancy information, so we know just how much and how efficiently we're using the GPU. Command buffer and barrier visualization, so we can easily pinpoint where we have bottlenecks in our frame, as well as ISA level instruction timings and VGPR usage information to really understand why some of our shaders might not be running as fast as we think they should. And this on top of a host of other features. Now, the latest release version, which is 1.7, also adds a new pipeline overview pane, and we've added a number of new overlays as well to help visualize data in whatever way you might want to. This includes by user events, by hardware contexts, by command buffer, or by render targets, and this is on top of the existing overlays that were already in the tool. The latest version also adds support for some of the newest products in the Radeon family, the RX 5500 and the 5300. And the pipeline information view has also been updated to indicate when shaders are being run via Wave32 or Wave64 on RDNA hardware. Now, you can always find the latest version of RGP at the link on this slide. Next is Radeon GPU Analyzer. So doing shader optimizations can be a bit of a time-consuming affair. For a lot of engines, there's an iteration cycle you need to go through of building the engine and your shader assets, running, analyzing the performance, and then making changes, and then doing this all over again so that you can analyze your gains or whatever your losses might have been. So RGA was effectively created to help shortcut this cycle. With RGA, you can simply export out your shader code and iterate through it in a static analysis fashion to really be able to quickly find and address bottlenecks. And once you're satisfied with your changes, just copy them back into your engine, build everything and verify one last time, and you're good to go. The tool offers compilation of shaders to a vast number of GCN and RDNA ISA disassembly, so you can target most common chipsets. There's also tools built in to help you analyze the liveness of your registers, so you can really see how your data is being used throughout your shader's lifecycle. And the tool has full support for D3D12 pipeline compilation as of version 2.3. Now, the last tool I want to talk about is also the newest one in our arsenal, and it is called Radeon Memory Viewer. This is a tool that allows us to capture memory information during an app's lifetime and be able to play it back and have a deep dive into the resource allocations at any point during the app's life. This is really useful for tracking a number of memory-related events like resource creation, seeing what our physical versus our virtual memory schemes are looking like, looking at memory paging. We can generate full history on any resource throughout the lifetime of the app and get a better understanding from those resources from when they were last accessed, or even be able to determine any special access patterns that might be going on. We can look at snapshots at different points in time and compare them to each other in order to help track down things like memory leaks or maybe other memory-related abnormalities. Now, Radeon Memory Viewer will be releasing soon, so do be sure to keep an eye out on GP Open to see when it goes live. And that pretty much wraps it up for covering a few of the new effects and tools that we're releasing on GP Open. So keep an eye out on the site. Thank you very much, and I hope this has been informative.